let's do this. 3x squared plus 3y squared plus 3z squared equals 10 plus 6y plus 12z. All right, thank you. That should be all I need that for. All right, so take a look at that equation. I'm going to tell you right now that this is the equation of a sphere, okay? This is the equation of a sphere. Now, you don't know that right offhand, all right? You may think you do because you see x squared, y squared, z squared. You're like, oh, well, wait a minute. We just learned that spheres have x squared, y squared, z squared. We're going to learn in a few sections that there are other objects that have x squared, y squared, z squared that are not spheres. So we have to be careful here. I have to tell you this is a sphere at this point. So this is the equation of a sphere. Everyone okay?
Yep.
I want to know the center and the radius. So find the center, and I want you to find the radius. And all we know is this. All we know is this formula, x minus, what was it? R squared plus y minus s. Wait, what did we use?
X minus h.
H, okay, sorry. It was L at the end. Sorry, I'm using the wrong one. H, L, squared, y, z.
Z was
minus L. Jeez.
Y was minus k.
Okay. Squared. No, it's not your fault. I'm just. Right, that's all we know is that if you have a sphere, this is the equation of a sphere with the radius of r and a center of HKL, right?
Yep.
So from here, we have to get to that formula. Like, we have to transform this into this, which you've done before. You just maybe don't remember. How do we get there?
Start by moving the 6y and 12z.
Move the 6y, the 12z over, and then what are you going to do? Kind of a factor. Complete the square. We got to complete the square. Yes.
You said in the start of the question that you said it's a sphere.
I'm telling you it's a sphere.
So that implies that it's not zero, so we could automatically just...
That what's not zero?
We can't move variables other sides if we cannot say that it's zero. So
You can move them. You can't divide or multiply by them. You can add or subtract them, but you can't multiply. Oh yeah, you can. If you have a variable, I'm allowed to subtract 6y from this side, regardless of the value of y. I just can't divide both sides by y unless I know y is not zero. But addition and subtraction is okay. All right, so I'm going to complete the square. So I'm going to move everything over. Let's get all our x stuff together. That's the only x thing I have, right? Let's get all the all the y's together. Let's get all the z's together. I'll leave the 10 on the other side.
the 10 wouldn't be considered part of x because it doesn't have the variable, right?
Yeah, that's right, because it doesn't have x on it. All right, anyone see, let's see, what can I do here?
Move y and take out
You want to start going after the y's? What about the x's? I mean,
can't you just divide by 3 across everything?
you want to divide everything by 3?
Can't you do that?
You can. Do you want me to? I can. Yeah. Y'all want to? It works out that we can do that here. It's not going to mess up anything except that's going to become 10/3. We're allowed to.
Couldn't we just...
Do you want to? Okay, but wait a minute. I'm going to challenge you on that. What if this was a 5? Would you still want to divide by 3?
No.
Probably not, right? So, what's that?
We said y and z equals 0.
That's what...
What are we trying to achieve? Maybe we should just back up and say, what are we trying to achieve here? Like, what is it we're trying to do?
You're trying to factor the y's, factor the z's, and then all the stuff over the other side.
But we're not factoring. What we're doing is like, that's just not the right terminology for it. What we're trying to do is massage this thing, okay? Massage it and make it look like this, Okay? We're trying to do algebraic manipulations to make the equation here look like the equation there. So we need to somehow make this look like an x minus h squared. This here look like a y minus k squared. This here look like a z minus l squared. Yes?
Could we then factor our y's out? Or like our y out of there and our z out of there? So we'd end up with a small binomial, effectively?
We don't want to factor.
don't wanna factor
That's
it?
not, no, because that's not what completing the square is. It's not factoring. So let me help, all right? We're talking about completing the square here right now. Yes?
To complete the square, don't we have to have a 1? In the
Okay, very good.
square?
So
Can we factor the 3 out of the y's and the 3 out of the 12?
that you can do.
The square of the y squared minus 2 and then the z.
Exactly. That's exactly what we're going to do. So the first step to completing the square is that you must have a coefficient of 1 in front of the thing that's being squared. I have a coefficient of 3 here. Can't have that. Coefficient of 3 here. Can't have that. This has a coefficient of 3, but I can't really factor a 3 out of x squared because there's no other term. So just let me write the next line, and then we just go from there. So 3 out there, 3 out here. Okay, do you agree with that? Yes? I pulled a 3 out of these two y terms. I pulled a 3 out of these two z terms, and I kind of left the x term alone. Now, what we see here in the parenthesis and what we see here in the parenthesis, those I can complete the square on. Now, you should have completed the square a lot by this time, all right? So I don't want to rehash the whole thing. We'll just verbally talk through it. What's the procedure for completing the square on this? Take what and divide by 2? Take that, divide by 2, which would be -1. You're missing a step. Hold on. Take this, divide by 2, square it, and then add and subtract it. Yeah? I'm going to write it down. Take y squared minus 2y. Okay, I'm going to take half of this number. Half of that number is -1. I'm going to square it. -1 squared is 1. I'm now going to take that 1. I'm going to add it and subtract it. There might be some of you in this class right now that want to take that 1 and add it to both sides. No? You can't because the 3 in front here, you can't do that. So it's better to add a hidden 0 in there and add the 1 and subtract the 1 at the same time. And then I'm going to do the same thing on the other parenthesis over here. 3, I'm going to go z squared minus 4z. Okay, I'm going to take half of this number, -2, and then square it, which is 4. I'm going to add that 4 and subtract that 4 right there. And then equals 10. Questions? All right, let me continue. 3x squared. The whole point of that, right, the whole reason we did that is because these 3 terms right here and these 3 terms right there are guaranteed to be perfect square trinomials, which means they factor to be something times itself. So that, in parentheses here, this turns into, these 3 terms turn into what squared? Y minus, y minus 1. If you factor just what's in green here, factor that out, you'll get y minus 1 squared. Now you still have a minus 1 here, right? You still have that minus 1 right there. And then plus 3, and then now you factor these 3. What should that turn into? Something squared, what? Z minus 2. Z minus 2. Squared, and then you still have the minus 4 back there. And you still have equals 10. Are you all with me or not? Yeah? Completing the square, yeah? It's been a while?
Yeah, it's been a minute.
What am I going to do now? I'm going to distribute the 3's back through. So this 3 is going to drop in front here, and it's going to distribute through. And then this 3 is going to drop in front here, and then distribute through to that -4. And I'll be closer to a result. So I'll have 3x squared. I'll have plus 3 and then y minus 1 squared. I'll have minus 3. I'll have plus 3z minus 2 squared. And then finally minus 12 equals 0. Everyone follow that distribution through there?
Yep.
All right. Let's take everything that's just a number, like any constants, let's take them to the other side. So minus 3 and minus 12 is minus 15. Go to the other side, you're going to get 25, aren't you? Yeah? So 3x squared plus 3y minus 1 squared minus, plus, sorry, 3z minus 2 squared equals 25.
Now we should divide by.
Now you can divide by 3. You could have done it earlier, but I was trying to avoid if not every number was divisible by 3, you would have fractions and it would be kind of ugly, but you could still do it, right? All right, so I keep going. Divide by 3. I'm going to rewrite this term, even though the 3 is going to be gone, but I'm going to write it like this: x minus 0 squared, because that's what x squared looks like really is, plus this is y minus 1 squared, plus this one is z minus 2 squared equals 25 over 3. The only reason I wrote this one is this x squared as x minus 0 is just to make it look like the formula over there, right? Yeah. To make it look like this. We're there, right?
Yeah.
What's the center of this circle? Or sorry, sphere. Center is 0, 1, 2. And then the radius?
25 over 3.
The square root of 25 over 3. Right? 5 over root 3. Okay. There are a couple of problems in your homework where you have to do that, where you have to, like, here's the equation, go find the center and radius. So I just want to do at least one problem with a little bit of completing the square. Last thing, and then we'll talk just briefly about the next section. Let's say you're in R3 still, right? You're in R3. And I want you to describe to me what this looks like. Or you can explain however you want to explain it. Raise your hand if you want to explain it. Hold on. I'm going to want everyone to be able to play. You haven't played, so go ahead.
I'd say it's more like a wall than it is a. Like
It's a wall, okay.
Instead of like a sheet of paper, it's like a brick wall.
It's a sheet. Okay, so instead of a flat sheet of paper, which would have been x equals 3, right? It's like.
Not wall, 'cause it goes past. It goes into negative. So yeah, it's more like.
So maybe we do it with this. Just without hurting myself. Let's just say this is the x-axis, okay? Let's just say it is. X equals 3, right here. This sheet, right? But everything that way, right? Because x has to be bigger than or equal to. So it's everything from here, this sheet right here, this plane, that plane right there, and everything that way forever. Up and down, left and right, right? So what is that? It's the YZ plane beyond 3, 3 and beyond, right? We call that a half space. A half space. Because it's half of the well, not, we call it a half space. It's a weird terminology. It's like this plane, right? But it goes that way forever, but the plane goes up and down and left and right as well, right? So it's like half of the space, right? Three-dimensional space, it's like half of it. Now you might argue, well, wait a minute, half would be if it went through the origin, right? Like if it went through the center of the origin, then half of it. Well, because we go to infinity in both directions, we just say half.
The volume's infinite.
It's volume, infinite volume, so we call it, and it's half space, all right? Kind of an interesting idea. Call it a half space. Now, how could I make this a brick wall? If you wanted this to be a brick wall, you could do some things to this. Do that, what? Put some bounds, some other bounds on it? Yeah, you could say something like less than or equal to 5. And then now you have this brick wall, right? It only goes from 3 to 5, but it goes up and down forever, left and right forever, doesn't it? Can you actually make a brick wall, though? I want a brick wall that stops and starts, and what could you do? Add some bounds on the other variables, right? So maybe I do something like y goes from, I have these inequalities in a weird way, but how about like 0 to 5? And then I could do something like z. Yeah, it's like a 5-foot wide wall. This would be the height. Let's make it like 2 tall. So now it's a little short wall. You know, there what we've created here is a solid box, haven't we?
Yes.
Okay.
It's one of those tripping boxes.
Yeah.
To make you trip on.
Yeah. Yes, sir.
Would it have a volume, say for a circle, and you put restrictions on that domain, could you theoretically put a square inside of it, like find the volume of a certain space inside of that circle?
Wait a minute.
Okay, so you have the volume, you have an equation for the
For
volume
sphere.
of a sphere.
Sphere, okay.
Sorry, of a sphere.
Uh-huh.
Inside, you can put restrictions, and that in those restrictions, you would be able to have a square inside of the
A
sphere.
box.
A box.
Okay. It's all right. All right. I just want to make sure we're,
Yeah, no, you're right.
yeah.
Is that correct?
If you have a sphere,
Yes.
and inside of it you have a box,
Yes.
yes?
So if you put restrictions in the formula,
Mhm.
you just make the sphere smaller, or you would make a sphere inside of a sphere? I don't know if that makes sense. We can talk about it.
Yeah. I mean, there's ways that you could work with inequalities and create a sphere where you've taken a box out of it inside. I don't know if that's what you're saying. There's a way you can write down a system, basically, of inequalities to make that happen. All right. So all of this is really just like, this is all still just like playtime in three-dimensional space. Like, we're getting into just making sure we're comfortable in the space, some of the notation, some of the language. We're not going to talk about calculus for a little while, all right? The calculus isn't going to come into play until we're somewhat comfortable like playing in this new realm. So now what we need to do is talk about vectors, because we've established what three-dimensional space is, we've established what points are, what planes and stuff look like, but now we need to talk about vectors. So we're going to move into the next section, 10.2. Raise your hand if you have some background with vectors. Okay, all right. So some of you have, most of you have. I'm gonna keep our discussion of vectors confined to the definition in terms of the calculus textbook, because in a more abstract sense, are there any math majors? There's math, right? So vectors are actually more abstract than this. They're not, they don't have to be arrows living in space. They can be something else. And so I just want to have a disclaimer here that I am only referring to vectors in this class in the traditional calculus sense of a vector. You could have, so, see, this is the tangent we can go off of. A vector is an object. Okay, that object just has to have a length and a direction. That's it, right? That's it. Now you look at that as arrows, and that has a length, and that has a direction. It's easy to visualize that. But from a pure math sense, your object could be a function. and its length could be the integral of that function, which would be the area under the function. You could, as long as you can measure something about that function, then you could call that the length. And then you just have to come up with some way of defining a direction for it. So however you want to define the direction, you can. So long as you have objects, some definition of a length and definition of a direction, then you have a vector space. Yeah, or a vector, sorry.
Within for say, you have just arbitrary wavy line. Your length would be your integral to find the length of the curve, and your direction would then that be the derivative function, correct?
No, what I'm saying is that a vector can, you're talking about specifically one way we could do it.
Yeah.
Sure.
With that one, would that be a?
I didn't say how we define the direction, right? I mean, we would have to determine how we want to define direction.
Okay.
But you have to have, see, we go way off here, and I don't want to go way off. That was the whole point. I'm disclaiming it, is because you have to have something that has a metric. A metric is something that's measurable. If you have to have a metric in order to have distance. And so in mathematics, not every space is what we call a metric space. Metric spaces are metric spaces. They have measurement. You can measure things in those spaces, but not every space has got a metric. So abstractly, vectors can be anything you want them to be, as long as you can somehow measure them, whatever that measurement is. It could be an integral, it could be something completely different, but it's got to be a well-defined metric, and then you have to have some sort of way of defining a direction. If you got that, then you got a vector. But for us, they're just little arrows pointed out in space, okay? That's what they are here. So I just want to make sure, this definition has an asterisk next to it, all right? So in this class, that's the definition of vector.
Cool.
An object that has a direction and has a length. That's it. Magnitude is another name for the length, or you could call it the norm. There's one exception. Those of you said you've seen vectors. There's one exception to there's one vector that does not play by these rules. Not the normal vector. The zero vector. The zero vector. Now I'm going to define it, but the zero vector is the vector that has a length of 0, which means it's essentially almost like a point, and a point doesn't have direction, right? So it would not satisfy this definition. So all vectors have this, with the exception of the zero vector. But I will talk about the zero vector later. All right, in two-dimensional space, this is what a vector looks like. It's just something we can measure the length of and the direction. Now, when we talk about direction in two-dimensional space, right, when we're in two-dimensional space, it seems very natural that a direction could be oriented where we take that traditional x-axis, something parallel to the x-axis, and measure this angle, right? That seems very natural that would be some way to get a measurement of angle, right, of direction relative to the x-axis. So whatever that angle is would be the direction. Then if we take the length from here to here and we measure that, right, we measure that, then that would be the length. So that's a vector. It's got a length, it's got a direction, right? Now, when we have vectors, right, they can be pointed in any direction, right? Change the direction, change the length. What about in three-dimensional space, though, right?
Would we have 3 coordinates to define the direction?
You have, well, think about this thing right here. It has a length, right?
Yeah.
Now I'm in three-dimensional space and I start pointing it somewhere. It has a direction, right?
Yeah,
Go.
break it up into the X, Y, Z.
Yeah, how do you talk about the direction of this? See, it's not on a flat sheet of paper anymore. So-
Angle towards the Y, angle towards the X, angle towards the Z.
Yeah, so you could, I mean, there's different ways of doing it, but if you have this here, I'm gonna hurt myself. Okay, I'm gonna lose a finger. So if I do something like this, right, then what I could do is kind of like project a shadow of this onto this plane, and then look at that angle. And then I could have put the shadow on that plane, and then got that angle. Or I could have done a shadow down and got an angle. Right? Do you see there's all like different ways to to kind of approach it. And it's not as simple as a vector in two-dimensional space, is it? It's not. In two-dimensional space, it's pretty simple. Got your vector, x-axis, there. Get your angle, you got a direction. But in 3D, a little bit more complicated. So we'll have to address that.
So do you only need two angles to define it, technically? Like a direction in 3D space?
In three-dimensional space, do you only need?
Two, like, angles, at least.
It depends on how you want to get it. But yes, you could say, if you're pointing down the x-axis in three-dimensional space, you could say, give me this angle and that angle, and then I would have a direction. Or you could have said, give me this angle and that angle, right? So just two, and then you need the length, the distance.
Yeah, 'cause I think
So two would be the minimum.
Yeah, I was thinking like polar coordinates, you only need one for each.
Exactly. So in three-dimensional space, it's called cylindrical coordinates, which is what we're going to do. We're going to do it. Okay, we're going to do triple integrals in cylindrical coordinates. So it's just going to be a new orientation, a different way to get from one point to another. But it's polar in 3D. Yes.
I thought you needed 3 because then the other one would be considered 0. Because
What? 3 what? You needed 3 what?
3 angles to consider the direction of a vector in 3D space. Because you would have, like at any direction that you point, you would automatically have 3 variables, correct?
I only need 2. Here, here. That's it.
But you would stay on the plane of that. Because you would have the x angle and then you would have the y to the line, but then you wouldn't have that z to get you out of that.
Well, the way that I thought of it is like you
No.
have, the angle that you're doing it is based off the plane. So when you have two angles, you're basically intersecting 2 planes. And you have a rotating plane, which comprises all space.
That makes sense.
Yeah, if you just imagine yourself pointing down the x-axis, I mean, imagine the vector's already there, right? And you want to, like, here's the vector, and I want to get to that vector, right? I want to point in the same direction. What I would do first is I would make my angle like this so that I'm at that same upward pitch, and then I just need to turn myself, and then I'm in that direction.
But you're initially starting at a point that is
At the origin, down the x-axis. So we have to orient ourselves initially somewhere. Yes. You have to, just like we do in 2D.
It's hilarious how much easier you staying there with the ruler made it to understand.
All right. Some language of vectors. This look familiar to you?
Yep.
When you have a vector, the big thing about a vector, the thing that makes a vector different from a line segment just connects 2 points. That's it, right? Give me 2 points, draw a line between them, that's a line segment. What makes a vector different?
Direction.
This is well, line segment kind of has a direction.
Yeah, but it has a specific beginning and an end in a direction. Well,
You said,
What's the difference between a line segment, that's a segment that connects 2 points together, and a vector?
One has direction.
when is the component of
Well, the vector, the arrow here does not imply that that continues. The vector, the arrow only gives you an orientation for direction.
what is continuous? When is it?
It has to do with the fact that if I give you 2 points in space and you draw a line between them, that's it. That's the line segment, right? There it is. If I move it like this, it's no longer the same line segment, right? It's a different line segment. Because those are now 2 different points. My fists are 2 different points. That line segment is different than this line segment. Agree? Okay. Now, forget line segments. There's a vector. If I move it here, is it the same vector?
yeah.
Does it have the same length and direction?
Yeah.
Yes. So the big difference between a vector and a line segment is that where it lives in space, for a vector, it does not matter where it lives in space. It's always the same no matter if you move it around. As long as you don't change the length and direction, it's the same vector, which is extremely important for physics because if you're applying a force to an object, right, if I drag this chair along, right, then you can imagine that the force is my arm is a vector. And I don't want to look at it as a line segment because if I move the chair and I look at it as a line segment, this is no longer the same line segment, right? It's now a different line segment. So we need some way of having something that would go with us and never change, and that's where the vector comes into play. I hope that kind of makes some sense. So this is just notation. When you have a vector, something has a length and a direction. This point that you start at is called the initial point or the tail, and then the point that you end is called the tip or the terminal point. In textbooks, they will use a bolded letter, usually V or U or W, to represent a vector. When I'm writing here in class, I can't write in bold, so I use that symbol right there over the letter. All it is an arrow that we cut the bottom off of, okay? And then we put our variable underneath it. Right, that's what that symbol is. So that tells you you're dealing with a vector. Now, equivalent vectors. This is what I was just referring to. How are we doing on time? Two vectors are equivalent if they have the same magnitude and same direction. So you see that vector? If I draw that vector, those are equivalent vectors. They are exactly the same. They're completely indistinguishable from one another because they have the same length and the same direction. And that works in two-dimensional space or three-dimensional space. So equivalent vectors have same length, same direction. Position does not matter. All right, now if somebody gives you 2 points on a flat sheet of paper and wants you to create the vector that goes from one point to the next, we have a formula for it. So I'd like to do this. There's 2 points, right? And what I'm going to do is I'm going to create a vector that goes from A to B. I could do a vector that goes from B to A, right? So I can have my arrow tip be here, like that, and have my tail be down there. I could do it that way, or I could do it the other way, right? So depending on which way I want to do it, the formula changes, because the direction matters. So I'm going to make up, let me see what these points. This looks like the point 2, 3. And this looks like the point, what does that look like to you? -1, -2. Okay. So those are 2 points in space. And let me get up to the formula here. What we're going to do is if we have a first point, x1, y1, second point, b, x2, y2, then the vector that goes from A to B, we write this way, A to B like that, is going to be written with, we call these, anyone know what we call those right there? They're not parentheses, or not angled brackets. We called them angled brackets. So you're going to write an angled bracket. You're going to take the x2, that's this x-coordinate on the point you're going to. You subtract the x-coordinate on the point you're coming from. And then you do the same thing for the y-coordinates. So let me bring this back up here. The formulas are all there for you to look in your notes. So if I want the vector that goes from A to B, I'm going to write an angle bracket like this.